Hey, hello, students. I just got a question on a real hard one here. I think it's a real hard one. Let me give it a try. It's number 18, number 49, and I actually looked it up on the hard copy version of the book instead of the PDF here. But let's take a look at it. And I think part of the reason it's hard is it says review problem, and that means it's going to take us back to previous stuff in our chapters, which would be our last semester, our Physics 121 with our mechanics. And it says here the top end of a yo-yo string is held stationary. The yo-yo itself is much more massive than the string. So I take it by that we don't need to worry too much about the string, because as this thing's going to unwind, technically its mass is going to decrease slightly. But I think that they're trying to say don't worry about that, because a yo-yo is so much more massive. It says it starts from rest and it moves down with a constant acceleration of 0.8 meters per second squared. And as it unwinds from the string, the rubbing of the yo-yo against the edge of the yo-yo excites a transverse wave, vibrations in the string. And then they're going to say both ends of the string can be thought of as nodes, even as the length of the string is increasing. And consider this instant when it is 1.2 seconds after the motion began. And then they get into a series of questions. But let me just kind of maybe take for what it's worth. So maybe here's the top of the yo-yo. It starts somewhere. Maybe I'll put its starting point right here, and it unwinds, and so later on it's down here, and it's going to keep unwinding. But an important part of this is what is the acceleration as it goes down. And they made it very clear that it starts from rest, so I'll say initial velocity is 0. Okay, and it moves down at this rate. So you could say something like this, and then this is probably the review part. If you go back and you say, okay, well, how long is the string? And let me just come back here. My picture, I gave it like a little initial distance and then started to unwind. I don't recall them saying anything about that initial distance. The top of the yo-yo string is held stationary. Okay, the yo-yo itself is much more massive than the string. It starts from rest. It moves down with a constant acceleration of 8 as it unwinds from the string, rubbing against the edge of the yo-yo, exciting transverse waves. Okay. Both ends of the string are nodes, even as the length. Consider the instant when it is 1.2 after the motion begins. Show that the rate of time, what if the mass distribution is kept the same? Did I miss it? I'm going to just kind of assume they mean the top end of the yo-yo string is held fixed. The yo-yo itself is much more massive. It starts and moves down with a constant acceleration. Okay, well, let me keep working here, but I am a little bothered by that small lack of information. But I think what I should have done in my picture is say the yo-yo, starts here, and, someone's just kind of holding the top edge and it comes undone. The reason I say that is because I want to do this. I want to say, how far has the yo-yo moved? This is our, I guess we called this our second kinematics equation, which was valid when we had a constant acceleration, which we do here. But what I want to say then is if we start at a position of 0, then the position of where the yo-yo is then would also be the length of the string. So let me put L here for the length of the of the string. Also, they made this at least very clear that it starts from rest, and then they also made the acceleration very clear. So I would have an equation that looks like this. The length of the string, or x, the distance it has gone down, is 1/2 of 0.8, I'll just go to put 0.4, t squared. Okay. And I'm going to maybe box this and leave it alone here for a second. Because, like I said, I think that's the review part here. Then as we get to the actual important part of this question, it says both ends of the strings are nodes even as the length of the string increases. Consider this moment, 1.2 seconds after release. Show that the rate of change with time of the wavelength of the fundamental mode of oscillation is this number. Okay, now the standing wave, and which is covered in this chapter, said that if you tied a string across here, that was length L, you could have this as the fundamental pattern, or this as the second harmonic, or this as the third harmonic. And my picture's going to get kind of busy there. But let's just look here at this fundamental. This should represent a half wavelength. So L equals a half a wavelength, or 2L is equal to the wavelength, or maybe I'll just say, well, yeah. But I can put these two now together. That then says, I'll put an L there, and so 1/2 of L is then equal, so well, maybe I should have made my connection here. So 1/2 of the wavelength, that's L, is 0.4 t squared. Or the wavelength changes, I'll bring the 2, of 0.8 t squared. Now, this brings me to the main question. Show that the rate of change with time of the wavelength of the fundamental is given by this number, 1.92. So they want a rate of change, and so let me take its derivative, and so the rate of change of the wavelength per time, and taking that derivative, I'll leave the constant alone, and then this would be a 2t. And so putting in the number that they said, what was it, how much time? 1.2 seconds. Let me grab then my calculator and go 0.8 times 2 times 1.2, and there it is. 1.92 is the rate of change, so meters per second is the rate of wavelength change. So that's A, and so A is really asking you to take a derivative of the distance equation, and I guess we actually, in retrospect of all this, we could have said that's just the, the velocity of it. That's the rate of change at which its distance is changing, okay? Oh, but we got a factor of 2 in there for the fundamental, so it's not quite just the velocity. Okay, now, as we go into B, is the rate of change of the wavelength of the second harmonic also 1.92 meters per second at this moment? And that's just kind of a yes or no, and I'm going to say no, and of course I would say no back here because there is this factor of 2 between the changing of length and the wavelength. If we were looking at a different harmonic, like say the second harmonic, so second harmonic, which would look something like this, then we would say L equals 2 lambda, and that little mathematical step we did there would be, differ by a factor of 2 because of the different harmonic. So every harmonic's going to come out differently. So I guess the short answer for B is no, because of these factors between the length and of the string as well as the velocity. I mean, the length of the string and the length of the wavelength aren't exactly a one-to-one relationship. There's some multiplication factor called the harmonic. So that would be I guess my answer to B. So then C goes on to say, the experiment is repeated after more mass now has been added to the yo-yo body. The mass distribution is kept the same so that the yo-yo still moves in a downward acceleration of 0.8. Okay, so still that same downward acceleration. At the 1.2 second point, in this case, is the rate of change of the fundamental length of the string vibration still 1.2 or 1.92? Huh. And I guess I'm trying to think of what the author's even after here. I mean, we put more weight on the yo-yo, and they don't give us too much detail, so we can't go too far back in the mechanics, but it still has the same acceleration. So, it's still moving at the same rate, and the rate and the wavelength happens to do with the length of the string. Huh. Now I know the speed has to do with the tension, so maybe that's what they're getting at. As I put more weight on it, that's going to change the velocity, which is also going to then have a corresponding change in the frequency of the vibration, but the length of it is, the length of the wavelength is connected to the length of the string. So the tension's just kind of affecting these two equally. That's what keeps the equation equal, but has no effect on the wavelength. So I guess I'm going to say no, and I guess that's kind of what they must be after here. As it moves down, the string vibration still equal. Yes, and it said explain. Is the rate of change of the second harmonic the same as in part B? Yes. Oh, and my apologies. I skipped, didn't I? I went actually to C. The experiment is repeated. No, what if the rate of change of the second harmonic is also. Now, I thought that was a yes-no question. They're not really asking for the rate of change in B, do they? What if? Is the rate of change of the wavelength of the second harmonic also 1.0? No. It's off by a factor of 2. I don't think they really answered it, but I'm going to go ahead and do it anyway. So let's talk about the second harmonic here. Maybe I'll just move this out of the way so I'll call it a wrap to this problem. I think technically I'm done. I didn't think they really asked me for what the rate of the second one was. But I am going to then come back here and say, okay, L is equal to the wavelength. So I would have, where's that equation right there? I would just tell that to a lambda, and it would be 0.4 t squared. And then, of course, when you take that derivative, you're just not going to have that extra, factor of 2 that we move over here. So it would be a 0.4, and then it would be a 2t, and the t would still be the 1.2. And again, we're just missing that factor of 2. So I guess I expect it to be half as much here. And so sure enough, I'll put those together. That's 0.8, and then times 1.2, and I'm at 0.96 meters per second is the rate of change of the second harmonic. All right, well, I hope that was a little insightful. I'm not sure that was that great of a problem, although I kind of like the conceptual piece of it, that the wavelength has to do with the length of the string, not so much the tension. and the review aspect. All right. Hope that helps. Take care.